guys.
Hi, everyone. Oh, someone forgot to change a background. Whoever that was, they're in trouble.
Our producer for today is... So hello and welcome, everyone, to another one of our Thursday afternoon sessions. For those that don't know who I am, my name is Steve Tracy. I'm the VP of Technical Services here at JL Audio. I am located in South Florida at our main headquarters. For joining me today, as always, I have Mr. Matt Mergenthal joining us from North Carolina. Please say hello, Matt.
Hi there, everybody. Thanks for coming.
And way on the other coast, we have Mr. Rob Haynes. Please say hello, Rob.
Hello, Rob.
You're hard to do it. So we have an interesting one for you today. This is kind of a more technical session. So we're going to kind of show you how to measure impedance using a max unit. We'll also give you some insight into what you can do with such information, as well as, the different types of measurements that we can get. But I don't want to take anything away from Matt, who's going to be guiding us through this process today. So Matt, why don't you go ahead and take it away?
Sure thing. And to note, the hurricane that just passed over Steve not long ago is now heading up the coast to me. So there's always that chance that I
want to share, man. We don't want to take it all for down here. We want to spread the love as much as we can.
Well, hopefully, if everything goes dark, you guys can take over.
You got it.
Rob, can you bring up the keynote for me, please?
There we go.
Slacking.
All right. So we're going to jump into it. And as Steve mentioned, we're going to get into using Max, the audio measurement system here today, to take impedance measurements. And we're going to talk about not only how to take those measurements, but we'll also talk about how to analyze the data and make sense of it. So first thing we'll do is we're going to go through some key terms that will help you understand and maybe bring some clarity to what we're going to talk about today. We'll go over what impedance looks like on a graph. We'll talk about how Max measures impedance from simple ways to more complex ways. We'll talk about what we can do with that information, and then we're going to jump into a live demonstration and a Q&A at the end for anybody who has any questions. All right.
Fantastic. Sounds like a good agenda, Matt.
Thank you, sir. So first things first, terms you should know. Sorry, I know we're creating a bar there. There we go. So frequency. I'm sure most people watching today already know what this is. And frequency is how often something happens within a period of time, which is measured in hertz. Right below that, we have impedance. So impedance can be described as a resistance to a change over frequency. So for example, here's a resistor, right? And the resistance, let me bring it closer so you can see it nicely. There you go. So resistance stays constant regardless of frequency. That's typically what happens with these resistors. However, if you measure a speaker like this one, the resistance will usually change depending on the frequency that you measure it at. Right below that, we have the impedance curve, and this basically just shows the speaker's resistance over frequency on a graph. And like I mentioned earlier, we'll jump into some graphs in a little bit and talk about that some more. We also have FS, which is also known as the resonance frequency. And the resonance frequency is the frequency that an object resonates at. So, for example, if you have like a bell and you strike a bell, it's going to ring at the resonance frequency of the bell. And a speaker also has a resonance frequency. So usually what happens with very little energy at that frequency, it'll result in a lot of output, just like the bell. Now we have a couple other terms. So we have inductance and capacitance, which are very similar. Inductance can be described as the opposition to change in current, and capacitance can be described as the opposition of change in voltage. And resistance maintains a constant resistance to voltage or current. So to kind of make those a little clearer, did you want to add something, Steve?
Yeah, I see the word inductance and capacitance. I think resistance is a term that's been floated around so much that it becomes commonplace. But inductance and capacitance, where else might you see that outside of the world of impedance? Where do you see inductance and capacitance?
Outside of the world of impedance, you said?
Yeah. So I mean, in audio, I've seen these words before, but I usually see them in some other application. Where else do we see something about inductance and capacitance?
Maybe
Rob, any ideas?
Yeah, sorry, I was typing a message there to Matt. And where do we see inductance and current capacitance outside of resistance?
Yeah.
For me, inductance, I think of heat. You have
See, I think of passive crossovers. I think of a high and low pass filter. Like you put a capacitor on a tweeter, and I put an inductor on a mid bass driver or something like that. So the terms inductance and capacitance are used in other areas, but what Matt's going to show is that they're related to an individual driver as well, that it has properties that are similar to what you'd find in passive crossovers, where it'll affect the frequency of that driver in some way, shape, or form. And there's really no difference when it comes to impedance. In this case, we'll be looking at its effect on voltage and current, as Matt just described. But the properties of inductors and capacitors are very similar to what Matt's going to share with you today. So this big world of audio, there's only a handful of terms that you need to know, and Matt's covering some really good ones now. So just wanted to share that you'll see inductor or inductance and capacitor or capacitance in other areas. Today, we're going to focus on its effect on voltage and current, on their effects on voltage and current as related to impedance. So didn't mean to throw you off there, Matt, but I just popped in my head.
I was actually going to go there when you asked where else I'd see them. I was going to say inductors and capacitors, but I felt like that was too easy. All right, so a good way to kind of and make an analogy of those things. So if you think of like a heavy train running down a railroad, resistance would be similar to if the brakes were engaged before the train began moving and they continued down as it moved down the railroad. So that's resistance. Regardless of what speed the train is moving, the brakes are resisting the movement of the train. Inductance would be more like the mass of the train from when it's at a standstill, trying to move that mass forward. So it would, try to resist the movement of the train because of the mass. But then once the train's actually moving, it would go the other way around, where now that it's in motion, it would try to resist the brakes that are trying to slow the train down. That mass is moving. So that's maybe a easier way to think of inductance and capacitance and how they work when you have a speaker that moves and it comes to a stop, and it's got that same kind of thing. So
actually, that brings up a question I've always had about this thing. I hear the term resistance all the time, and I also hear the term impedance all the time. And oftentimes I've heard them interchange, where people talk about the resistance and or impedance of a given thing. And I've always been confused. Why do we have two terms? Like, what's the difference?
Of impedance versus resistance, you said?
Yeah.
So the resistance, we could actually show this, but the resistance is usually something that's measured when you're measuring DC. And impedance is something that's usually measured for AC. So the speaker does have a DC resistance and an AC impedance, and as well as so does the resistor. So we can kind of demonstrate that, which may help to bring clarity to that.
Well, so that brings up an excellent point, actually, and thank you for the softball. I appreciate it. So the resistor, the thing you're measuring, it has some type of electrical resistance of sorts, and whether you use DC or AC will determine if you're measuring resistance or impedance. So if you're using a DC measurement system, you'll wind up with DC resistance. If you're using some type of AC measurement system, you'll wind up with the impedance, which is frequency related. It's a resistance related to the frequency. So that resistor that Matt's holding, you can actually measure the impedance of that, but it'll be a straight line. It's not changing over frequency. But the speaker, by the nature of it being a speaker, is going to change as we look at this impedance over frequency. It's kind of what gives it its sound and its flavor. There's a lot of information we can learn from just looking at the impedance. We were kind of having a chat about that earlier, but I'll let Matt go. Sorry, Matt. Just keep interrupting like I always do.
With everything that Steve said, inductance, capacitance, and resistance are kind of what make up impedance. So first things first, we're going to take this resistor and we're going to put it in our multimeter here. Rob, can you blow me up so maybe they can see a little better? Thank you. So now I have these alligator clamps, and I just clipped them onto the end of each resistor. And you can see that we're at 9.9 ohm. So it's a 10 ohm resistor, but it actually reads 9.9. You can see it fluctuates back and forth. So that's the DC resistance of this resistor. So now I can measure the DC resistance of this speaker. So if I clip these terminals onto the speaker, we can see that our DC resistance is just under 4 ohm. Looks like it's kind of going up and down slightly, 3.8 to 4, in between that range. And you'll also notice that we talked about impedance and changes in frequency. That right now it's the speaker's still, so the what you're reading is about 4 ohm. But as soon as the speaker starts moving, that measurement changes drastically.
And that tells us all over the map. It doesn't lock into a single value.
Right.
For
Yep.
those that don't know what we're looking at, if you look at the voltmeter, you'll see as he's pushing it, just to make sure. Yeah, there we go. Now we can see it.
No problem. So as I'm pushing on the cone, I'm actually generating electricity when I move the speaker cone, because there's a magnetic field and it feeds that energy back into the multimeter. So the multimeter is going crazy because it's trying to look for a certain voltage and current that it knows, or a certain current and voltage drop that it knows, because it's a closed system. It knows from the multimeter, the signal goes out, it goes through this device under test back into the multimeter, and it uses Ohm's law to figure out what the DC resistance should be.
So, Matt, if I may just jump in real quick, you made a statement. I just want to make it clear for a second. Your light went off. When you're working with a meter like the one that Matt's showing right now, inside that meter, it's using Ohm's law. It's basically like a giant calculator, and it's sending out a known signal and measuring the difference between the variables that it's controlling. So in this case, it's sending out voltage and current, and it's sensing the change in that and calculating out the resistance using Ohm's law. It's a known condition that it is, and that's what Matt means by a closed loop. What he's going to show you with Max is very similar to that it's a known system. It's sort of a closed loop for the first type of measurement, that we're sending out a known signal and we're measuring the change over frequency for that known signal. So there's really not much of a difference between the meter that he's using here to measure DC resistance and the meter that's behind it, the bright yellow one, that's going to measure AC instead. So.
Right. Excellent. Thank you for adding that, Steve.
No problem.
So at this point, can you jump back to the keynote, Rob?
Poof, there it goes.
All right, so we talked about all these terms. So now we're going to get into the actual graph and kind of show what we're looking at here. So in tune, you can see that we're actually looking at the impedance graph. On this one, the y-axis represents impedance in ohms. So, resistance, sort of, but it's impedance. And then the x-axis on this one represents frequency in hertz. And then here we go. So here we have a impedance measurement of this speaker here. It's not an active measurement, but it's a, one we captured. So what's going on here, Steve? It looks like we got some different peaks and different movements. What does all this mean?
It looks like it just drew a pretty line on the screen.
Right. All right. So first we have inductance. And as we go up and start rising towards the peak of that, this is inductance. And then on the way down, it actually is capacitance, where it goes downward towards the bottom. At the very peak, we have what's known as the resonant frequency, so the FS. And on this speaker, I believe it was about, actually, this isn't the measurement from this speaker. I'm sorry. It's a measurement from a subwoofer. But the measurement there, I think, is at 35 hertz, right, roughly about. And then after that, we have more inductance. And as it starts to get higher and higher in frequency, you see that it takes a lot more, the resistance goes really high as the frequency increases. So that means that at higher frequency, it's going to play less and less loud, which makes sense because it's a subwoofer.
That does make sense. So as you go higher in frequency, higher resistance means less output from your amplifier in most cases, right? And that would result in a reduction of output, which is why, like a subwoofer doesn't play high frequency really well, because of whatever's going on with this impedance thing.
Yeah. And then what you'll notice here, this I find really interesting. This is considered a 4 ohm speaker, which we just measured with our multimeter. Actually, again, this was the subwoofer, but the only place where it's actually 4 ohm is right there at the bottom where that line goes across the graph. Everywhere else, it's above 4 ohm. And I find that very interesting that at different frequencies, it's not 4 ohm. Mainly it's between 55 hertz and maybe 85 hertz is the only place where it's actually 4 ohm.
I would contend that it's rarely 4 ohms.
Yeah.
So I think we have a lot of discussion about this, and I don't want to get too confusing with any of this stuff, but we would call this a nominal 4 ohm load. So we'll just say, just call it a 4 ohm speaker, because there is a range of frequencies that this driver is likely going to be playing, that it's going to be in and around 4 ohms. So for casual conversation and ease of installation flexibility, we would call this a 4 ohm speaker. You'll also see on the spec sheet for drivers like this that there's going to be a DC resistance or an equivalent resistance. And that's simply for point of reference. So like when Matt took his fluke meter and he connected it to the speaker, it was reading effectively as close to a DC resistance as it could for a speaker like that. Now, there are some other things that are affecting it, but for the most part, you're just measuring the coil of wire. And the reason that it jumped around as it did is, as you may know or you may not know, I'm just going to do a brief explanation. Sorry, Matt, if you go long, it's on me. It usually is. When you wrote this, pausing for a moment, forget impedance for a second. When you have a coil of wire and you run electricity through it, it creates a magnetic field. If it's alternating current, the frequency will change that magnetic field. It'll kind of change its direction from a positive to a negative, or whatever you want to consider, right? When you take that coil of wire and you attach it to a cone and you drop the coil inside of another magnetic field, when you put that signal in there and alternate it, alternating current, it's going to want to push up or down because the suspension keeps it from going any other way, and it'll move it, the piston up or down, and you got yourself a speaker. Very basic explanation of that. But the same thing is true in reverse. If you pushed on the cone of that speaker, you can measure voltage on the output. So if you could take your voltmeter and put it on the output of, or the terminals of a speaker, by gently, cautiously pushing on the speaker itself, you can show a voltage. You can even light a light bulb if you really wanted to, depending on the speaker. So what's basically happening is when you're measuring the DC resistance of a speaker, there's a little bit of energy from the magnet that's affecting your measurement. And as you move the speaker, now you're creating additional voltage and current that's pushing back against your meter, and your meter has no idea what to do with it, which is why the values jump all over. A lot of conversation in the chat about the meter showing OL, or overload. And what's happening is it's seeing voltage and current coming back to it that it has no idea where it came from, and it's freaking it out a little bit. So it's going to show you this error value, basically saying, this is not what I'm expecting. In terms of what's happening there, you're not going to hurt anything. The meter is almost certainly going to be able to absorb whatever you send back to it. That's not the issue. And it's not an issue for your amplifier because it's intended to drive an AC load, no problem at all. It's just an abnormality when using DC resistance on your meter to try to figure out something that's really an AC intended circuit. Does that make sense?
Yeah, I think so.
Okay, cool. Well, just wanted to get that all out there. Hopefully that didn't confuse everyone too much.
Sometimes you think you're helping and it goes the other way.
I know, but I think making the connection of what a speaker's actually doing and how it's making sound, right. And it does that in reverse, which is really cool. But when we're measuring a different type of variable in that same circumstance, it might show some very odd things. And I think that's what is causing possibly some confusion on the in the chat regarding the OL on a DC measurement for a speaker. So
I got you. Yeah, no, I think I think what you just did was pretty good. It was clear. I get it. So what can we learn from these types of measurements? So we can help determine issues with the speaker, right? So if I have this speaker here and another one just like it, I can compare one against the other and see if there's a big variable between them. If they look almost identical, chances are they're probably both okay. But this doesn't tell you everything about the speaker. It really only tells you about the moving parts of the speaker. So for example, if there was like a crack in the cone, you might not be able to detect that with impedance. So, there's other types of measurements that can help you determine if the speaker's actually bad. But if the coil was frozen and it didn't move and you hook up an impedance measurement to it, you'll know right away that it's no good, right? The other thing that it can tell you is if something's touching the speaker's moving assembly. So like if you were to install this speaker in your door and you're putting the door panel on and the door panel makes contact with the actual speaker cone or the surround or any part of the moving assembly, that'll show up in the impedance graph and you'll be able to check that. It's actually really helpful, especially if you already have a max unit that's out in the bay for testing electrical signals. It makes it really easy to check if something's touching the speaker. It's also helpful for enclosure design. So anyone who's designing enclosures, when you take this impedance measurement, it can give you really good data to find out other parameters using other softwares and stuff like that. And at the very end, you can learn about speakers, learn what this speaker is capable of doing in impedance and where the FS of the speaker is compared to the FS of maybe a smaller speaker. So it's really helpful just to learn about different speakers and what they can do. So on top of that, I think we're going to jump into the live measurements now, unless you guys have anything to add.
Love live measurements. Josh Collins is making fun of me saying overload when it's open loop, and I pointed out it both are wrong.
So what we got here is we have a pair of TRS impedance probes. JL Audio does sell an impedance probe and an XLR probe and a TRS probe, which you can purchase. But this is just the probes with a pair of alligator clips that I've added to them.
Matt, can you show that TRS tip for a second there? Because I don't think everyone knows what that actually means.
Okay.
What does TRS actually stand for?
Stands for tip, ring, sleeve. So tip, ring, sleeve.
Oh.
And
okay. Making sure everyone knew. And it's like a 1/4-inch jack, like a headphone jack.
Exactly. Yep. So I'm going to go ahead and plug this into the side of our Max unit here. Okay, so we're plugged in there. So now we have to go into the Tune software. So bear with me 1 second. I'm going to pull up our Tune software. Share that for Rob.
He wasn't kidding when he said hands-on today.
Yeah, no doubt, right? Lots of stuff.
All right, so here we have Tune software open. We're in the impedance graph right now. So now
How'd you get there, Matt?
So in the top left corner of the graph, I simply selected impedance from our graph type combo box.
Okay.
And I've made it full screen. You can do that using the panes button in the top right corner of the screen. So what we need to do in order to make these probes work, we have to turn on what we call impedance mode. So to do that, I have to go to the measure settings, which opened on another screen. Here we go. And we're going to go over to the measurement setup tab. And on the right-hand side, when you have Max connected, you'll see this little area that says TF1 impedance mode. And if I turn that on, you'll actually see that it routes signal to these two channels. Now, those channels, the XLR inputs, actually will not work at all when you're plugged into when you have impedance mode hooked up like this. So
just for the record, everyone, the graphic that's represented there, Matt, if you don't mind going back to that measure setup for a second.
Sure.
That graphic in the upper left where it shows the XLR inputs, we are working on an improvement that'll change that to represent what's actually going on because you're using the other side of the device, and it was just easier for us to get it done this way. And obviously impedance measurement is not something you're doing every single day. So we're working on the graphic improvement on that. But what Matt is saying is absolutely true. Those XLRs will not work as they normally would when you're in impedance mode.
Yeah. Right.
I think it's also important to realize, Matt's in measure only mode. He's not connected to a DSP product, no VXI, tweak, MVI. So, don't let the targets fool you. This is part of the actual measurement system with Tune and Max. You don't need to be connected to a VXI, tweak, or MVI type product to do these types of measurements.
Right on. Thanks for that, Rob.
So what I'm going to do here, I'm going to close out of that window. I'm going to connect my probes, my alligator clips, to both sides of the speaker. So connected to the positive and the negative. And then I'm going to go ahead on my graph here. I'm going to press the play button on my signal generator. And you'll notice I'm actually playing pink periodic noise, which is totally perfect for our measurement. We can actually, if I go to the input combo box, I can play our data. And here you can see our impedance trace of this speaker.
Sweet.
And what's neat is this is real time. Like it's actually in real time. I guess clapping doesn't make a big deal out of it, but if I touch it, you can see that it's live. So this is exactly what I was referencing when I mean you can put a door panel or a grill on top of a speaker, and the second it makes contact with that speaker, you're going to see a change in that impedance measurement.
So, Matt, you've shared that comment with me before, and I'll confess, it took me a little while to realize how I could actually use this. So, like if I put my speakers in the door and I put the door panels on, and then I measure impedance, it's going to look a certain way. It might look exactly like this. But if I push on the door panel, it shouldn't change. If it does, the door panel is actually hitting the speaker. That's how you can tell. But
Yeah, for sure.
If it was hitting the speaker and you didn't push it, the impedance would look pretty stable like it is right now, right? So if Matt could, if he could rest his hand or like take a pen or something and leave it on the piston, it will stabilize and show an impedance measurement. If you don't know if that's good or bad, right or wrong, it's the change that happens when you push on the door panel by seeing it fluctuate the way his measurement was a moment ago. That's how you know that there's something that you should probably address.
I'm wondering if the sales guys are still cringing, like Scott said.
Why? Why would they cringe?
He said
About you pushing on the speaker?
Earlier in the chat, Scott said the sales guys were cringing when I push on the speaker cone. So I'm wondering what happens when I do this. All right, so pretty basic, right? So what I'm going to do is I'm going to capture this measurement, and I'm going to hit the space bar to capture it, and I'm going to call this ZR8. Okay. So what I want to do now is I want to actually take the alligator probes, and we're gonna calibrate the measurement, and that basically allows us to just position the data on screen where it's totally accurate. And I made a mistake already because I've already calibrated it and I didn't reset it. So we'll pretend that it was not calibrated.
Whoops.
And we will start over. So what I'm going to do here is I'm going to pause the signal generator, and I'm going to connect my resistor to these probes. So now I have the probes connected like that, just like we did for the resistor or for the multimeter. And we know the value from the multimeter. It was about 9.9 or 10 ohm. So it's very close. So now I'll hit play on my signal generator again. And now you'll notice our impedance of this resistor is actually straight across the graph.
Look at that.
There is no rise or fall in the resistance because it's a resistor. It resists the change in voltage or current regardless of frequency.
All frequency equally resisted.
Most frequency. At least in the audible range for this one.
All visible frequencies equally resisted.
Yes. So what we can do here is we can see on the graph, we have that little flag, and it tells us that our actual measurement is 10.38 ohm. So it's a little high. So I'm going to use a hotkey here, and I'm going to hit some buttons, and I'm actually going to lower that on the graph. You can see that my value is down to 10.03 now. And you could also do that up here in the impedance combo box. You can manually adjust it right here. So now we're right at 10.01 ohm. You can go a little lower. 10 point. Oops, too far. All right, we're right at 10 ohm.
Two things I want to ask about, Matt. First of all, what's that box next to your cursor, that little flag-like thing? What is that?
That's a new feature that is going to be launching in our next version of Tune software, which should be available very soon.
Very soon is a good way of putting that. That's excellent. So we call those data flags or data flags, however you want to put it. And it basically is sharing the same information that you'd see in the info box up in the top, but it puts it right where your cursor is. So if you want to see the data a little bit easier, right where your eyes are, that's there. Toggle that, hitting the F key, F for flag, right?
Yeah.
The other question I have is, you were just calibrating that measurement based on the resistor value. It reminds me of what we do, like if you're using a USB microphone, that you have to calibrate that to read SPL. Is it the same kind of thing?
It is very similar. Yeah, we're just calibrating the value on the screen. It's
Okay,
not
so that
required.
it makes sense compared to other values, but otherwise the shape doesn't change. It's just a position of it, right?
Exactly. It's not required at all. It's just required if you want the exact measurement, the exact measured data. If you want it to be perfect, then just grab a resistor and calibrate it, and you're good to go.
Gotcha.
Same thing with the USB mic. You don't need the calibration file. You don't need to calibrate it for SPL, but if you choose to, that's up to you.
Perfect.
So moving on from here. So now that we've calibrated it, I'm going to go back up to the top right corner in the input combo box, and I'll right click and select set calibration. And now you'll notice the value actually went to 0, but on the graph, you can see it says CALD, like calibrated. So now we know that our measured data is calibrated. So I could then pause the signal generator, and I'm going to go back to measuring the speaker again, and let's see what changed. And obviously, the change that we made was very little, not a large change by any means, but we'll be able to see how it changed with the calibration versus no calibration.
Oh, it's way different, Matt. It's so obvious.
So it's very, very similar, and you can see why it's not required to calibrate it. But there are other ways that we can make it even more accurate. And usually you'll see the calibration value really make a bigger difference on like a high frequency driver, like a tweeter or a mid-range. Those typically will have a greater effect. Mid-bass and subwoofers, it's going to be very, low, very small difference.
But Matt, I remember when I was first playing around with the impedance measurements with Max early on, some of the demonstrations I did, it was like I ripped up little pieces of paper and sprinkled them on a mid-range, a little 3.5-inch mid-range drive, just sprinkled them on there. And as each one hit, I could see the fluctuation in impedance pretty visibly. But
Sure.
I did the same thing on a big-ass woofer, and very little, if any, change at all because of the relative change compared to the mass of the speaker. With the smaller drivers, the difference was much closer, so it showed up a little bit more. And I think that might be what you're referring to. At higher frequency, some of these fluctuations and deviations are going to be more prevalent.
For sure, yeah. This has a much heavier mass and cone assembly and everything than a smaller driver would. So yeah, there's a lot of things that'll show up. So I think at this point, what I want to do is something fun. I'm going to connect my probes here to some other speakers that I have that I'm going to play with. And I want you guys, Steve, Rob, and everybody in the audience to try and guess what I'm connected to without seeing it, based on the measured data. And just to be clear, you can kind of get an idea from this data that we have on screen. This has to be a low frequency driver because it's got a very low FS. This one's about 50 hertz roughly. And then it rises up and kind of tails off, so it doesn't play too well above probably 2K. So based on the data that you see, I'm going to change to some other speakers, use that that data to try and maybe come up with what we're looking at here.
So the driver that's there has a peak at low frequency, then it has a pretty pronounced rise at the top end, and we would call that a woofer, right?
That is a mid-bass woofer.
Okay.
Yep.
Okay. So let's see what you got here.
All right. So this one, see what we got here. I'm gonna start easy.
It's a tweeter.
Now, why would you say that?
Well, because the high frequency is off the chart, right?
Nope. Total opposite. Any other guesses?
I'm looking at where that peak is, and that looks like around 60 hertz, so 54 hertz.
Mm-hmm.
So
Maybe like a 8-inch subwoofer.
So I'm thinking like a 6-inch subwoofer with like a pretty gnarly coil on it, something that's got quite a bit of inductance on it. That's what I'm thinking.
All right. Well, it looks like Scott Williams got it right. It's a 10W3, 10TW3 in a sealed enclosure. So what happened? The actual enclosure made the peak of the impedance rise
up
because it's in an enclosure. So it's not as low as it would have been if it were free air.
And for the record, the coil on a TW3 is pretty massive, so that's why you see that rise at those higher frequencies. TW3 is not going to play 5K very effectively.
It doesn't play 300 very effectively.
Right, exactly.
It is cool,
and that's why. That's one of the reasons why.
It is cool how with the size of the coil and that increase in inductance that we can see how the driver itself has that natural almost crossover built into it.
Yes. Yes. And in some of our earlier Evolution product, we actually took advantage of the inductance of the voice coil to eliminate some componentry from the passive crossover network. And we took advantage of that rise as part of the speaker design. Just a little tidbit for you.
All right. I'm moving on to another speaker here.
Ooh.
So some guy, Manville Smith, pointed out that the peak moved higher in frequency because of the enclosure, but the actual FS of the sub is lower than that. And that's how Matt tripped us up. We're looking at drivers, not entire systems. So,
Well, you don't know what you're looking at, so you're going to have.
We have no idea. Yes, this is true.
All right. What are we thinking about this one?
Well, after you duped us on the last one, I'm going to be quiet.
No, I need some answers.
Some sort of 6.5-inch mid-bass, mid-range driver.
Spot on, Rob. That is spot on. It's actually a C5 650. So there you go. Rob got it spot on.
Everybody watching is like, can I buy that from you?
All right.
I do miss those.
We're going to the next one here.
Okay. I guess maybe a 5 1/4 or something like that.
Oh, before Matt answers, let's see if anyone in the chat chimes in. We do have it up on the Facebook feed now. Oh, we have Glenn says a C7 350.
Nope. Good guess, but he's close.
I'm gonna go with a C2 350 then.
I'm trying to think of all the product that Matt took home with him.
Now you got to think of product that Matt had a long time ago.
So Scott says C2 350. I'm gonna go C5 400. The old 4-inch C5 mid-range.
Bob is on a roll.
Check him out.
And you know what? To give him credit,
400.
Glenn's got it as well.
I've had this for years, many years. All right, so now it's only going to get harder from here. So I hope you guys are ready.
Is that an appropriate time for a Michael Scott? That's what she said joke, or I watch The Office every day, so I'm always looking for moments for that's what she said.
Nice.
All right, bear with me 1 second as I get my probes connected.
There's another one opportunity there, Rob.
You guys are too much. All right, here we go.
Ooh, look at that. It's got a massive coil on it. That I can tell you.
Yeah, look at that rise.
Some interesting stuff.
Scott Williams said it looks like my house curve.
So lots of questions, lots coming in. Multiple 8W7. Brian says 13W7. Manville just says it's big.
All right, so
I'm going to guess W7 just because I know how large those coils are.
So hold on, I got to make this fair. These last three are not specific JL Audio products. So just give me the size, and if it's in an enclosure or not in an enclosure, try to give me that without the product specific.
All right, I'm guessing not an enclosure. The resonance is pretty low on that. It's a subwoofer, pretty stout coil on it. Lots of inductance there. I don't think it's an 18 like Josh is thinking. I'm thinking maybe a 12 or something.
All right. Well, I'm going to show you what it is. This is a 8-inch. They call it a subwoofer. It's more like a mid-bass kind of subwoofer. It plays about 40 or 60 to 300 hertz.
What size is it?
It's an 8-inch.
Okay, because Glenn and Manville both guessed an enclosed 10-inch sub. So I was wrong on the enclosure part.
Yeah, this thing's from 1989, I think.
Ooh. Where'd you find that thing?
In the garage.
I thought that was before they invented impedance.
Yep. All right, next one here.
Wow, that's a goofy looking one, huh?
Yeah, it sure is. Now, I guess I would ask what might affect the. He said,
we're all there, Josh.
What might affect the peaks of a speaker?
Yeah, I think I know what that is, but I'm not going to say. I want to see what everyone else jumps in.
All right.
So we have a two-way bookshelf speaker from Glenn. Brian says a Aura bass shaker.
Interesting.
Manville wants to know if you can make the scale wider at the bottom.
We're at 20 to 20K, but we can go like that. Some of these comments in the chat.
So we're looking at the blue trace, right?
Yep. All right, everyone give up?
Yeah, let's see what it is.
All right, Glenn got it right. This is a two-way bookshelf. It's small. It's really tiny. It's like a 4-inch and a tweeter. And
I was picking up on the tweeter part of it. I didn't realize it was a 4-inch.
Yeah, you can tell it's a tweeter because it doesn't have a lot of inductance at high frequency.
Right.
But I think what's happening is the passive crossover inside of this enclosure is killing those peaks. It's taking them way down. So there's a lot of things going on through that passive crossover.
Well, with passive crossovers, inductors and capacitors and resistors and all the things that you're trying to measure here. So yeah,
that's
it'll
right.
Screw it up a little bit.
I got one last one, and I think this one will be good. Let's see. I'm going to switch back to my alligator clip here. Alligator clip. Aha.
Ooh, multiple peaks.
All right, what do we got here, guys?
Pretty blue line.
Let's see some guesses in the chat.
I feel like Matt is priding himself on stumping everyone like my daughter does at Share Day, where she purposely describes her share item in a way that no one's going to know what it is.
No, I'm honestly just having fun because the measurements that I'm seeing, it's cool to see how different one speaker is compared to another speaker.
So Glenn says 3-way. Manville says it's something ported.
Okay.
Yeah, I think Manville's right about the port. Looking at the low frequency stuff, I'm trying to figure out the top end.
C2 690TX.
No, this is not a JL Audio speaker.
Manville just trying to be as right as can be with the port.
Yeah.
Let's see if it's tuned to 42 hertz. Yeah, right about 43. It looks like.
Oh, 43. You're way off, Manville. That's
all right. I'm going to show. So what we have here.
Yeah, okay.
So you'll notice it is ported. Here's the port right down here. So if I cover the port.
See, that's awesome. I like that.
You could see that it's no longer ported because I covered it. So an FS actually moved down in frequency. And then as soon as it goes ported again, what happens is it actually splits that. And at the lowest valley of that, in between the two dips there is the ported tuning frequency, like Manville said in the chat. What's also interesting is the tweeter up top. You can still see the rise from the tweeter and then the fall. So what's cool about this speaker is I can actually disconnect. You can actually biamp it, so I can actually disconnect some of these wires here. Let me see here for 1 second. There you go.
Yeah, so now it's just a woofer.
Just the woofer, exactly. And then we could look at just the tweeter. Hold on a second. I think I got some extra resistance in there. No, it's just got a. Wow, that's a big one.
Well, you would expect that on a tweeter, that it just goes off the chart at low frequency.
Yeah, no, that's very true. So yeah, so we don't start.
I wonder, Matt, if there's a capacitor inside the enclosure on that tweeter too.
I believe there is. Yeah.
So that would add even more on that rise there.
Mhm.
Yep. It would be like a sharp high pass filter causing that.
Yep.
Cool.
So actually, Matt, can you go back to the woofer measurement?
Yeah.
It's a great illustration of sealed and ported and how the resonance is different, and it's not necessarily good or bad. It's just the visibility of the differences I wanted to show. Change the scale a bit. There you go. So that's the ported one, and you can see that the actual resonance is of the port at that point. You can see the individual, the lack of resonance is at the port. You see what the driver is doing at the two peaks. And when you get rid of the port, go ahead and get rid of the port. So the effect of the port is largely minimized as best as Mac can cover it. And then now you're just looking at the driver's resonance itself. So that's pretty cool. That's how, if you're trying to figure out the tuning frequency of a box, you put the woofer in the box, you do an impedance measurement, and you can find it out pretty quick. There's other ways to do it as well, but this is a pretty effective way.
Right, and that's not the real FS of the driver in free air. That's the sealed enclosure effort.
Correct.
So once you took it out of the enclosure, it would then change to whatever the free air specification would be.
Indeed.
All right,
cool.
so I got one last thing to talk about. Get rid of this enclosure. And what I want to show is some other types of impedance measurements. So what we did so far today is we did a 2-wire impedance measurement where we take 2 wires, we've calibrated it using a resistor, and we connected it to our speakers, and we got a pretty good measurement. But there is one other way that you can actually get a more accurate measurement. Well, actually, there's 3 other ways, but it's considered a 4-wire impedance measurement. And effectively, what the difference between a 2-wire and a 4-wire is that in this case, both voltage and current are measured through the 2 wires, right? So whenever current flows through a pair of wires, you have voltage drop. So that changes the measured data slightly. So what we're going to do is we're actually going to have this other probe here, which I'll show it on camera. It's an RCA on one end, and the other end is banana clips. So all it is an RCA to banana clip, so we can put different ends on it. And this allows us to measure the voltage externally. So we're still measuring the current through the clamps, but the voltage will be measured through a separate input to max. So that allows us to measure the voltage at the speaker terminal itself, which means there's going to be less voltage drop on this wire because there's less current flowing through it. Does that make sense?
You get a cleaner, more accurate measurement because you're isolating things.
Right.
Okay.
So I just plugged this into the reference input on max, and I'm going to first we have to calibrate it just like we did with the resistor in the first case. So I have to actually connect the TRS probes to send the signal to the resistor. So we can see that our TRS probe that's already here is calibrated. What I'm going to have to do is go back to our measure settings, and we have to route a new transfer function engine. And to do that, we need to send signal from the line level input, which is right here. The default setting is internal analog loopback, so you may have to change it to external input. And then the reference would be the same reference signal, XLR number 1, that we already have selected here. So that's the signal that we're using, that channel of max to do that measurement. So then I'm going to go ahead and hit play, and I'm going to connect my other alligator probes to this probe here. Let me grab my visual. Here we go.
A lot of alligators, dude. You should come back to Florida.
Yeah, there is a lot of alligators, huh? Whoops. All right. So now we can see that there is a difference between the green. Oh, it helps if you actually connect it to the other side. There we go.
Details.
So now there's a difference between the green and the blue, right? So the external voltage is at a different level. So I'm going to first zero this out. Now, for math reasons, we have to actually change the gain of this input first. So I'm going to switch to two graphs here, and I'll go to the meters and gains panel. And I'm going to go to my analog reference, and I'm going to lower the gain value down.
And why are you doing that?
Sorry, I can't do that here. I have to do it on the impedance graph for now. But effectively, you want to use that meters and gains panel first because it gives it has to be in order for the calculation for the math to work. So you lower the meters and gains panel first, and then you make your offset here. Because these measurements are just for me, just to play with, I'm just going to do it here for now, but you'd want to go to the meters and gains panel first to lower it there initially. And now we can see that both of our measurements are right at 10. We're at 10.07 ohm. So I'll go down just a little bit more. Okay, so now we're at 10 ohm for both the transfer function, the impedance, and the TF2 are both at the same level. So then if I then remove these alligator clips and I put them back on a speaker, and we'll go with a smaller speaker this time. So this is our C5 mid-range. And I just need to grab these clamps, switch them out. All right, so now connecting this here.
Yep.
All right, so here they actually look very similar. But you can see as we zoomed in, there are some main differences in this area here at lower frequency and up top. They're a little bit off. And I think this connection is barely holding on. There we go. So there are some small deviations between those two.
Mm-hmm. So why would you go through the trouble to do that?
Well, if you wanted the most accurate possible measurement, then you would want to measure the voltage externally.
Gotcha. Okay.
If these measurements are just to see if something's touching the speaker in the door, it's not required. This is just for, if you're serious about taking impedance measurements, you want the most accurate data, a 4-wire impedance measurement will always be more accurate. And there are two other methods of the 4-wire impedance measurement, but in order to do those, you would need it basically doesn't use the TRS probe that's connected to max. What happens is it measures the voltage and the current externally. So right now we're measuring the voltage through the external voltage sense cable, and then the current is being measured through the TRS cable. But in the other applications, you could either use a current probe, which goes over the speaker wires and actually measures the current as it passes through those wires, or you could use a shunt resistor, which allows you to measure voltage drop across that resistor, but that would be in line with the measured data. Now, why would you want to do those things? Because it would allow you to actually measure the speaker at a higher excursion. So you could actually play the speaker loudly and measure the impedance at that loud level. So it is.
If I understand right, Matt, the method you've showed so far, the TRS, the phono jack, the 1/4-inch plug with the alligator probes, straight up 2-wire, the signal for that to drive the speaker is all coming from max.
Correct.
Right. And then for the 4-wire that you just demonstrated, the current is coming from that same probe, but now the voltage is being measured from the speaker side as a separate measurement.
Right. It's being measured through that RCA cable.
And the other two methods allow you to drive the speaker with a separate amplifier entirely, something outside of max, and simply use the XLR inputs of max to measure both the voltage and current separately on the outside.
Right, you would measure both separately. So the TF1 impedance mode that we turned on earlier, that wouldn't even be used for those setups.
Right on. Okay, so it'd be like a transfer function between the voltage and the current on the two XLR inputs.
Yeah, exactly. You could do XLR inputs or XLR and RCA and so on.
Gotcha. Cool. Okay, so that allows us, like you said, to drive the speaker as it would be driven in a real application and kind of see what's going on in, I guess you call it real time, right?
Right, exactly. Yeah.
Very cool. Very cool.
I think that just about sums up the live demonstration, unless anyone had anything they wanted to see specifically while it was hooked up.
I wouldn't pack it up just yet. Let's see if there's any chatter that comes from it. But Matt, this is kind of a deep topic, this measurement of impedance. And I know we only scratched the surface on what you can do with this, but I think it's really kind of neat that the system that we've put together with Max allows for this type of measurement for some of this higher level detail. I love that idea of the troubleshooting for speakers in the door to see if there's something hitting it. I really like the fact that you can see the effect of an enclosure on a woofer. We had talked about the speaker in a box, speaker out of the box, how the resonance will shift on that, speaker in a sealed box, speaker in a ported box, and you can see the changes in that. You can learn a lot about what speakers do just by looking at these curves. And the little Jeopardy type thing that you did there, where you challenged all of us to figure out what each one was. I think that was interesting because you could see certain shapes and get an idea of what might be going on. And I think for the most part we kind of hit right around a lot of that information. We didn't all get it right, but whatever, right? We could see that with the inductance rise at the top end, we can pretty assuredly say that's not a tweeter. And when we saw that rise at low frequency, we could pretty assuredly say that's not a woofer. It's when everything's all thrown in the mix, like your three-way system or whatever that was, that had all this stuff going on. That becomes a little bit more challenging.
Yeah, for sure. It can definitely be interesting, but I think the data by itself doesn't mean a whole lot. Like if you were to take an impedance measurement, just to take it, it doesn't mean much. It's just telling you something about the speaker. It's like this speaker's a 4-inch speaker, but by itself that doesn't really mean much.
Right.
How powerful is the speaker? How much power can it handle? What's the mounting surface? Where can it get mounted? So it's just one measurement. And there, like we showed today, there are definitely some cool things that you can use these measurements for or learn from the measurements.
Exactly.
But by itself, it's.
So Manville made a comment that I think is an important one. It kind of speaks into what you were just talking about. The curve by itself is just a curve. Comparing it to something else, like a state before and a state after, or as Manville's saying, a tweeter that is good and then one that you suspect may not be. If you look at the impedance difference between a known good and the current one, you can get a good idea if this thing's performing within spec or not. So if you see radical differences between what a driver that is working really, really well and one you're wondering if it's working well or not, you can take an impedance measurement of the suspect one and compare it to the good one and see that difference.
Yep.
No more dead on arrival claims unless you have a verified max impedance measurement out of the box when you open your product.
Exactly.
Scott Williams added that would be useful in system diagnostics.
Absolutely.
Yep.
Absolutely.
I think it's cool that we can figure out the tuning frequency of an enclosure.
Yeah. There are other ways, but this is a real simple one. You just plug that thing in, connect the probes to the woofer, and play some pink noise, and off you go. You'll see it pretty closely. And even with the relatively small screen size that we had, that one guy, that Manville guy, Manville was very easily able to find out where that null point was in the impedance response, and said that's where the tuning frequency is. And he was obviously 42 to 43 hertz. He was right. He was right on the money just by looking at that thing, and I think that's awesome. So for a lot of times when we talk about Max and the measurements we can take, both acoustical and electrical, a lot of people think that it's just for like esoteric and high-end stuff, but it's really not. It's for all aspects of it. Like Scott said, it's useful for system diagnostics. And there's a lot of SPL guys that if they're trying to make sure that everything is dialed in and their tuning frequency is consistent on each one, you could really hone in on where those peaks and valleys would be on the impedance plot and make changes as necessary to really dial in your system. So it's very, very powerful.
Absolutely. And it also doesn't take very long either. You can see
No,
how
that-
set up and took
The full
measurements.
wire took a couple of seconds just to follow along with what was going on there. But when we describe it as measuring voltage from an external source, and then sending that into the system in some way that could be plotted, then it made total sense.
Yep, for sure. So,
Very good stuff.
any questions pop up?
No,
So I did. Scott, said it was definitely a topic he'll need to work on. I think it is for all of us. In the chat, I did post a link to a really good article that Matt wrote that's hosted on our help center that will, again, step by step, walk you through the process of taking these measurements that we've gone through today.
Yep, absolutely.
Yes, that Manville guy. I always make fun of him.
So great comment from Scott. And I like this because, when we talk about measuring and system tuning, a lot of people think sound quality. But, he says, I think once the SPL guys realize how helpful Macs can be, which is absolutely true. I love seeing guys like Drew Jones out there using Macs to get max output of their subwoofers.
Exactly.
When
No
you're
pun intended.
out in the lanes competing, and every fraction of a dB could be the difference between winning and losing. And what we're able to get by analyzing stuff with Macs that we weren't able to see before. This is not just, of course, it's going to make your car sound great if you follow the steps and sound quality and all of that. But the SPL world too, man, we can get significant output gains by being able to analyze and correct issues, typically acoustical issues or time-related issues in the vehicle, thanks to the Mac system. And then especially with stuff like this, it's that extra step to get everything out of your system.
The Star Trek references continue with Manville. Phase, the final frontier. Resistance is futile, and phase, the final frontier. This is too much. What a way to go out, huh? Matt, I want to applaud your efforts here to take, as Rob kind of alluded to and was sort of mentioned by Scott, a fairly complex topic. It's a little bit hard to get your head around and kind of make it, I think, a little bit more understandable. Mm-hmm. And if you have a Macs or access to something like that, you can actually start taking these measurements and just playing around. I think that's great. And, I appreciate you putting the effort in and explaining the total of 4 different ways of measuring impedance, even though we only, really covered 2 and showed very effectively 1. That one measurement type that you showed is probably suitable for most applications. And I think it's Absolutely. Great. So thank you, Matt. And thank you, Rob, for, managing all the behind the scenes stuff. And thank you, everyone, for watching and contributing as you often do. So I'm going to say goodbye until next time, and we'll see you soon.
See you, everyone.
Thanks, everybody.